Let's let's quickly revisit the climate change context in which we are trying to understand all these feedbacks. The best thing we are relying on is the CO2 concentration data, which is shown here in this smoothed out magenta purple color. We have gone from 280 or so at the beginning of the Industrial Revolution to now over 415. In fact, this one ends in 2016. We are increasing by about 4 ppm per year. At the same time, the temperature has increased by over 1 degree centigrade. And we have talked about how the seasonal cycle of CO2 is strong. We have smoothed it out. Interannual variability exists as well. But the temperature variability tends to have these internal variabilities like El Nino, La Nina. We talked about Pacific Decadal Oscillation, Atlantic Meridional Oscillation, and so on. They are loosely referred to as oscillations. So we don't know whether they are because they are not exactly periodic. Then you have to understand where the irregular period comes from, etc. Nonetheless, just to keep in mind that CO2 traps more energy, and that energy gets distributed more than 90% into the ocean for evaporation, for melting glaciers and so on, and then the internal feedbacks, El Nino and so on, do occur, and they are not going to go away anytime soon. The broader idea of the change we saw again was this map from IPCC fifth assessment report, which looked at all the regions around the world, continents, oceans, small islands, and polar regions, and looked at physical systems, biological systems, human and managed systems, and synthesizing all the evidence that exists. It is clear with various levels of confidence that humans have affected all systems on all continents and all oceans, including polar regions, right? Just an example of how closely we are all connected. Even Antarctica now has COVID, so basically every continent now has COVID. So this human travel and the way we transport not just our pollution and our land use change and fisheries impacts and so on, we also transmit all the viruses and bacteria as well. So there we are. For doing past climate responses to perturbations, as we said, we need a good sense of the perturbations themselves, the magnitudes, and we need to interpret the responses by having as much data at as high a spatial and temporal resolutions as possible. So many sources exist. We are going to just touch on a few. This is what is called wind-blown loess, which is basically fine-grained dust which can get transported long distances or short distances based on how fine they are and how strong the winds are blowing and so on. So they can give you evidence of monsoonal variations. For example, this is a loess mountain in China where actually people build homes and live in them. So past climates can be interpreted from these using various techniques. Typically, you need to date it so you know how long ago a particular evidence comes from, and then you need to extract other information like what the temperature could have been, or what the location could have been, what the CO2 amounts could have been, what the amount of rain could have been, and so on and so forth. So for that, we combine ice cores, as we said, snowfalls, more snowfalls on top, traps air bubbles, dust, pollen, etc., and keeps compressing and produces nice ice cores with stratifications which can be used to go back in time. The bubbles can be analyzed for atmospheric compositions at those times, including carbon dioxide, methane, nitrous oxide, conductivity, which is the amount of dust, for example. If you have a very cold glacial period, in general, the Earth tends to be drier. dust amounts tends to be higher. So that those sorts of things are recorded as well. And you have ocean core, sediment cores. So production of biotic and abiotic sediment that drops to the floor and keeps collecting also forms stratified layers, and it could be biological signatures in the upwelling regions, river runoff signatures, sea level signatures, and so on and so forth. We also have tree rings which record seasonal changes in temperature and precipitation, corals which record sea levels and temperatures, and calcium carbonates have crystal structures that correspond to temperature variability and sea level variability. Ice cores we already mentioned. Speleothems, so groundwater that seeps through and creates these stalactites and stalagmites in caves, can keep very good records of isotopic signatures of precipitation and water vapor variability and so on. So very useful as well. And of course, coming into modern times, we have satellites flying mostly from the 1970s onwards, now collecting all those essential climate variables that we looked at. There are tons of in situ measurement systems now as well, especially in the ocean, as we saw before briefly. Here again, global time series networks, volunteer observing ships, anchored moorings that stay there for a long time and beam data, floats that go up and down, as we talked about, the Argo floats, and so on. And you have the global observing system, which tries to monitor air quality, carbon dioxide in the ocean, monoxide, methane, ozone, temperature profiles, clouds, aerosols, and so on and so forth. Okay. The geochemical techniques have been incredibly powerful in interpreting past climate records in terms of dating them and understanding the fractionations or isotopic variabilities that record proxies for temperature and so on. So depending on the half-life, they can serve various time scales. So rubidium 87, uranium 238, and so on are the parent isotopes listed here. I won't go through all of them, but we will revisit some of them along the way. C14, for example. The daughter isotopes created are like strontium, lead 206, 207, argon, radon, nitrogen, with those particular half-lives, so they are useful for several tens of millions, more than 100 million, order 100,000, less than 500,000, order 50,000 carbon dating, and they are useful for dating granites, rocks, basalts, corals, and anything that contains carbon, like the fossil fuels that we are burning. Okay, so we will see how that works a little bit later, but to look at one example, look at O18 and O16. So O18 is basically, I briefly mentioned in the last chapter, oxygen has O16, which is the most abundant, 99 point some percentage. There are small amounts of O17 and O18. O18 has been used extensively. The schematic here shows that the ocean has a certain fraction of O18 and O16. Obviously, O16 tends to be much more abundant in the H2O. When evaporation happens, because O18 is heavier and requires more energy, the water vapor in the atmosphere is preferentially full of O16, and it's already depleted of O18. And as it's transported in the Hadley cell and the mid-latitude storm tracks and so on, precipitation then tends to drop O18 because it's heavier. So by the time water vapor is carried to the polar regions and or being dropped as snow, it has been heavily concentrated in O16 and heavily depleted in O18, which means the ocean tends to be heavily concentrated in O18, relatively speaking. Okay, so depending on whether you're looking at ocean creatures, sediments, phytoplankton, forams, and so on, or you're looking at ice cores, you can use formulation, this one, delta O18, which is the fractional amount compared to a standard sample, a standard measure stored somewhere very carefully, to the sample you're getting from somewhere in the ice core or a foram or a phytoplankton sediment or whatever. And they are typically they are measured as parts per thousand, not percentage. So you have an additional zero here in the bottom. So percent with the additional zero. Percent is part per hundred. Parts per thousand is this symbol here. Because the amounts are so small, we typically measure them in parts per thousand. Okay, so we will look at a little bit more of the data in the next podcast. I'm trying to keep these typically to 10-12 minutes because your attention span tends to be of that order. So I hope it's easier to listen to, but if you want longer podcasts, you can send me a message from the YouTube channel. Okay.